Sir,
Yeah.
so can we say that oscillators are signal generators?
Yeah, that's what I'm trying to say. Yes. Good. Okay. So, so as what's her name? Yeah, Dhamira. So, so as Ajita was asking now, are oscillators or signal generators? Definitely yes. All signal generators that you use in your laboratories to give as an input. Say for example, you will have a circuitry, right? Say for example, you have a diode here, and then you have a resistor, and then you have a sinusoidal signal generator, right? What is this inside? What is that you have inside is it is nothing but an oscillator circuit, an unstable circuit that starts generating the sinusoidal waveforms due to the oscillation of electrons inside the semiconductor devices. So yes. Now, if you look at similarly, what are the other sources of generation of analog signals is your motors, your generators, they are all different sources of analog signals. Now, coming to the digital signals, what is a digital signal is? Digital signals, they are discrete in nature. What do you mean by discrete is they will have only two values. Either they will have a high value or they will have a low value. Now the immediate question that will come is what do you mean by high and what do you mean by low? Normally, say for example, in this kind of circuits, we say that you have a positive values here. All these are positive values and all these are negative values. So, and you have an additional value, which is a zero value here, 0 volts. So which one you will consider it as a positive? So that decision, whether uh, it is high or low, that decision is taken by the design engineer based on the system he is designing. What do you mean by that? Some engineers might consider that I will take 0 as my low and the maximum value, say for example, plus 5 volts is what is the oscillation if I have, then I will consider this plus 5 volts as a high. There may be engineers who will try to design their circuit saying that I will take the negative 5 volts as a low and positive 5 volts as a high. So you will have a signal something like this oscillating between plus 5 and minus 5, and designers might take that I will take this value as a low and this plus 5 as a high. So it all depends on the engineers who are designing the system what to consider as a low and as a high. But ideally speaking, nowadays nobody is considering the negative values as a low. We start from zero. Why we start from zero is because grounding your circuit, it makes it easier if you consider it as a zero. Otherwise, what you have to do is you have to you have to design positive symmetry circuits in order if you consider the negative values also. So now, how is this digital signal change? We saw here that analog signals are generated by with the help of audio signal generators or motors and generators. Now, how is this digital signals are generated? Digital signals are generated from DC voltages only. How? Say for example, say I have a voltage here. I have a DC voltage here. Again, this is a time variation here and I'm having a DC voltage here. Right? DC voltage means it will be a constant value. So if I represent the output of the DC voltage, it will be normally through a DC battery, right? DC battery or even a 5 AA cell battery that you use can be used. Now, and if say for example, I'm giving it to a resistor, if you look at what is the voltage across the resistor, that is also going to be a DC voltage like this. So your input is also a DC voltage, your output is also a DC voltage. Now, instead, what I do here is I'm going to replace this particular line using a small switch. If I'm using a switch and I'm switching on and off this particular switch, what happens is your output gets disrupted now. So the constant DC voltage that you are getting in the previous case, now when I close this particular switch, I will have a positive line. When I open this particular switch, I will have a 0 voltage. And when I again close this, I will have a positive voltage. Likewise, I can generate these discrete voltages. I can generate these discrete voltages. So this is how you can generate the digital signal. So we saw how to generate an analog signal. We saw how to generate a digital signal. Now, yes. Now, how is this particular, what are the different types of switching circuits? What do you mean by a switching circuit is, here we are using a switch, right? Please note that these are not manual switches. These switches, the switching on and off, they are controlled using switching circuits. You will have a separate circuitry that makes the switching on and off. Normally, these are electronic circuits which is employed by using the transistors or MOSFET transistors, right? So what is the working of this transistor? Say, for example, I am giving plus 5 volts here on the biasing voltages. Based on the signal that I am giving here, only the conduction will take place from this point to the ground potential. So you give a voltage here, you give a DC voltage here, your transistor gets on. You don't give a DC voltage here, your transistor is off. So similarly, you use electronic circuitry to design these switching circuits. These switching circuits are very important because based on the kind of switching circuits, we classify our complete digital systems into two different types of circuits. One is called as a sequential switching circuits and other is called as a combinational circuits. In case of sequential circuits, there will be a feedback that will go from output to your input here, right? In case of a sequential circuits, which means that there is going to be a memory element that will be inserted in this part of a circuit. We will see in detail about these sequential circuits later on. So just for time being, try to understand that in sequential circuits, there will be a feedback that will take place from your output to your input. And at the same time, you will have a memory part also. In case of a combinational circuit, you will not have the feedback. Your output just depends on your input at that particular present time only. Whereas in case of a sequential circuit, your output will depend on the present time of your input, present time of your input, and at the same time, past input also. So that is the difference in case of a sequential circuit. Say, for example, if you want to have a past input, then what does it mean? It means that your previous output must have been stored somewhere. So that is why I said that there will be a memory element in your sequential circuit. Okay, so all memory storages, everything, they are sequential. Combinational, your output will happen based on the present instance of your input. So say for example, now if I am giving a 2 volt input, for this 2 volt input, there is going to something happen to this, right? Say immediately if I change the voltage to say for example 3 volts, my output will change immediately. That is what is a combinational circuit is. Whereas in case of a sequential circuit, my output will take into consideration my present input, which is 3 volts, and at the same time, my previous output, in fact, corresponding to this particular 2 volts. So that is the difference between sequential and combinational circuit. As I said here, sequential circuits, they normally have memories, which is a very important thing you must remember. They have memories, whereas combinational circuits, they do not have memory. This is a very, very important thing. Obviously, you need not memorize this. As you start working on sequential circuits and combinational circuits, this particular concept will be inbuilt. Now, why digital? Right? What are the applications of digital? We saw the applications of analog electronics such as audio amplifiers, etc. In case of digital circuits, what is the application? The mobile phones or cell phones that you are using, they are all digital. Nowadays, 100% almost every component that you use is digital. For example, digital camera, GPS, and then your televisions, everything has become digital. At least television was analog few years back, but nowadays everything has been digital. Now, when you consider digital systems, how this particular course is going to, because digital systems is the future, and you take any field of application, you take communication field of application, everything is digital. You take banking systems, business transactions, everything is digital. Even the traffic control, it is digital. Your space guidance, missions, medical treatments, weather monitoring, internet, industrial applications, scientific applications, everything is digital, right? So uh, now, in case of a digital signals, we said that they have discrete inputs, right? So we said that their outputs are going to be discrete. Discrete in the sense either they have a high value or they have a low value, right? Now, the question is, what do you mean by first discrete? When I say discrete, it means that there is a finite number of elements. As an example, in alphabet letters, we have finite letter of elements, right? A, B, C, D, etc. till Z. So 26 letters we have. You take a playing card, there are 56 playing cards. So these are discrete numbers, 26, 56, they are discrete numbers. Whereas if you take an analog signal, as I said, if this is an analog signal, if I ask you how many points are here, you will definitely say that there are infinite number of points. So discrete means that the number of values or signals or the magnitude must be a finite number. Now, how do you represent these digital signals? Normally, an analog signal, you know how to represent, right? If you consider an electrical signals, we classify them as voltages and currents. Your voltage can be a sinusoidal voltage, or it can be a transient voltages also. You can have a transient voltage like this. Similarly for currents, right? Similarly for currents. So voltages and currents, they can have the same kind of response. Normally, when you say signals, all these voltages, currents, electrical signals, they are continuous in nature, right? So when you say these digital signals, they are discrete. As I said, they have only two values. Not only two values, to be very precise, they can have finite number of values. They can have 26 values. They can have 28 values. So that is called as a discrete. But what we are going to do is we are going to consider a discrete system or a digital discrete system which is going to have only two values, which is 0 and 1. And that kind of a system, that kind of a discrete system that has 0 and 1 are called as, we call them as either as a binary system or we call them as a digital system. Okay, and this 0 or 1, this is unique values. If you represent, normally analog signals we represent like this, right? Instead, nowadays we are going to henceforth we are going to represent our digital systems as discrete systems. Discrete systems in the sense either it is 1 or it is 0, 1 or 0, right? So this either it will be 1 value or it will be 0 value, whereas here this may be say 1 volt, 2 volt, 5 volts, 7 volts, infinite number of values we have, and these values, zeros and ones, we call them as bit, right? The combination of bits, you must have studied the combination of 4 bits, we call them as bytes. And then if you consider the complete group of bits, then we call them as a binary system, or in fact binary codes. We call discrete signals that gives you a particular information through a group of bits, we call them as a binary codes. Now, as I said, what is a digital signal? Digital signals can be generated from analog signals, which are represented as with discrete values as 1 and 0. Please note that 1 is not a magnitude. 1 corresponds to 5 volts of analog signal. 0 corresponds to 0 volts of analog signal. So, which means that, I mean, immediately you can ask me whether it should be strictly 5, whether it should be strictly 0. No, not required. Normally what happens is we will have a threshold. What do I mean by threshold? Threshold means this is an analog scale here. Obviously, this is time. In the analog scale, say for example, from 0 volts to say for example 1.5 volts, we call them as this is a threshold value here. We call any voltage range during this particular thing to be 0 volts. Similarly, the maximum we have 5 volts and to a minimum, say for example, till 3.5 volts, right? This is a threshold we are going to have here. Any voltage that we experience in between these voltages, we are going to call them having a value equivalent to 1. So it's not 1 volt, value equivalent to 1, right? Now, the immediate question is, what is the values intermediate to this particular range, these particular ranges? These ranges are called as high impedance range. High impedance ranges, high impedance range in the sense they are neither 0 nor 1 and it is of no use in the digital systems. Your circuit has gone into a high impedance state in the sense your circuit is in a state where it is not ready to accept any value. That is what this means. Now coming to the some of the best examples of a digital system. Your digital system, as you know, your being a computer science students, your digital computer that you are experiencing, laptop, everything is a digital system, right? Your complete memory unit, your processing unit, your inputs, outputs, your USBs, your pads, your mouses, everything, keyboards, all are digital systems. But practically, if you look, what are the limitations of having a digital system is practically whatever we use, everything is analog. Say, for example, the speech that I'm giving you is an analog signal. Your heartbeat is an analog signal. Your BP monitoring is an analog signal. Everything, the power supply that we get from a plug point is an analog signal. So practically everything is analog signal, but we want everything to be processed in digital signals, right? We will look at why digital here in the next portion here. So what is that we are trying to say here is whatever practically we are having, everything is analog. And what is the output that we want? Output we want is also analog, but the intermediate processing here must happen in digital, right? So why so much fuss? Why should we, when everything around us is analog, why don't we keep handling in analog only? What is the need for us to convert them into digital and then back to digital to analog? Why should we do this? Or should we do this really? Yes, it is very much required for us to handle everything in digital for multiple advantages, n number of advantages. So some of the few advantages of having a digital system is number one. So there are many advantages that I'm going to list here. So we will just go through a few advantages here. It is easier to design, right? How easier to design? Because we have studied, when we studied analog signal, that is the number values or number systems, the technique that we studied to solve a number system is, say for example, what is, I'm just finding some space to write, so I'm not scrolling down the notes. If say for example, we have x squared plus 1, right? If you plot this, this is going to be something like this. If I have x plus 3, right, we are going to plot like this. So what are these x squared, x plus 3, and then the factors of this? All these things are a part of algebra, right? So this is a mathematical technique that we know to solve our analog thing or analog continuous systems. All these are continuous variables. So similarly, in case of, because we have only two variables here, in case of a digital system, similar to analog algebra techniques, we do have an algebra technique in digital system, which we call it as a Boolean algebra logic, right? Which is much simpler when compared to the analog mathematical techniques. In case of what are the other mathematical analog techniques that you know is, you might have studied whenever we say about analog, right? So even I try to represent the continuous signal like this, and then I try to mark it as a time scale. It is not mandatory that you must have only the time scale here. but it can be a frequency scale also, right? So likewise, you can do this analysis of analog signal either in the frequency domain or you can have it in the time domain. At times, what we used to do, we used to transfer the time domain signal into some other domain, which we call it as a complex domain, right? So say for example, this will be a real part here, this will be an imaginary part here. So we do an analysis of the same signal here. So this same signal gets transformed into some other signal like this. So what we do here, we convert the time domain signal into some other domain signal. Why we are doing? Because mathematically it will be easy to solve such a signal in this domain. After we solve, again we go back to this particular domain. You must have studied the same thing in Introduction to Electrical Engineering, right? So there are different transformation techniques in analog systems such as Z transform, L transform, wavelet transform, Laplace transform. Likewise, there are n number of multiple transformation techniques. So all these are definitely, they are complex in nature when compared to the digital systems. In case of a digital system, all you have is simple Boolean algebra that handles just zeros and ones. So that is why it is easier to design any digital system when compared to analog system. Second is programmability. What do you mean by programmability is you are very much familiar in writing C, C++, nowadays Java, Python, all these languages have come, right? All these languages over the years, if you look, the way they have evolved, they have become very, very simple. When we used to study, we used to have DOS programming, DOS. You must have heard this. Then came C, C++, right? And then came Java programming. And then there was Oracle also. And then nowadays you are writing Python codes. And then now there are more codes like this. Say for example, microcontroller based codes are there. Android programming codes are there. HTML codes are there. Now, if you look at the way they have evolved, they have made things simpler, right? So all these languages, when comparing with this, you had Unix also. Still, I think Unix programming is there. So Unix, DOS, that is what we were all introduced when computers came for the first time. So nowadays you are handling this Python. So what is that they have evolved? Because their simplicity in programming has evolved. Similarly, in olden days, if you still have an analog TV, then what happens is if there is an upgradation that you need to do for your TV, all you need to do is you have to replace your TV. Say, have you heard a company called a Solidaire? Solidaire. Solidaire is a TV company. Nowadays, it doesn't exist. It's a TV company which was famous in 1990s to 2000, right? So they produce analog signal. They had, if you want to change a channel, then there is a dial knob that was there to change the channel. And after this, there came a button system where you can change the channels. And then came the remote system to change the channels. So that is what you are having to change the channels now. So if there is any upgradation that you need to do to your television, you have to completely replace it. Nowadays, what is happening, if you connect it to a Tata Sky, if they want to update their channel list, all they need to do is when your setup box is on, they will simply download a code and then it will take some time to get it installed, and then you are good to go with the latest TV listings. Right? So that is how we have evolved over a period of time. So the programmability has improved because of the digital systems. At the same time, the storage of information has become much, much larger. This has even led to a new field of study. What is new field of study? Data sciences, which everyone wants to do. Data mining, which everyone is fascinating about. Artificial intelligence, machine learning. All these are based on the advantages of processing in the digital systems. Cost is also very less. You all know, as IC costs, inside your IC you have millions and millions of transistors. I mean, since you are a computer science students, the Pentium P5 P7 processors, the IC that you are having, they work under say 50 nanometer technology, right? Nowadays people are working even at 8 nanometer technology. What do you mean by this 8 nanometer technology is this 8 nanometer represents the transistor. You might have studied about transistor, right? But you will have, what are the three terminals of a transistor: emitter, base, and collector. So in case of a MOSFET transistors, you have gate, source, and drain. So you will have a gate here, source, and drain. The length of this, there is a channel between the source and drain here. The length of this channel is the 8 nanometer value. When I say 8 nanometer, it means that this channel length is 8 nanometer. So people now, the size of the transistors, they decide on the channel length. So 58, when I say 8 nanometer, the size of the complete transistor is much smaller. When 5 years back, they were operating at, say, for example, 30 nanometer technology. It means that your transistor size is larger. So now, as the transistor sizes are reducing, the number of transistors that you use in a unit area inside an IC or a die is increasing, leading to more functionalities with reduced cost. And then obviously the speed, the processing, it takes place in milliseconds and microseconds. The accuracy and precisions are much greater when compared to the analog system. If you are unable to get an output in an analog system, what you need to do is you have to keep on tuning. Say, best example is when you drive in your car, if you are trying to find out a radio station, it is about analog tuning actually, right? If say for example at 103.8, if say 101.2, some station is there. Exactly at 101.8, if you don't have a digital remote or something, you will have to adjusting through a small knob that you will be having. You will have to adjust this particular knob such that you have to set 101.2. Lightly, because if you are if you're riding on a bumpy road, this knob might get vibrated and then it will change to a different channel. So your the error in case of an analog system is much larger when compared to the digital systems. Now, at the same time, as the last few advantages of a digital system, they are more versatile and reliable. What I mean by versatile is they can even operate under extreme temperature conditions, extreme operating conditions. Their functionalities have improved a lot. Now, I mean, if you in your age, I think you were all 2000 born, I believe. 2002 born, I believe. So if you look, when you were born, just before you were born, there were Nokia, this button phones were there, right? It looks bulkier, so much big it will be there. You can only talk, so that is called as 1G. And then, sorry, you can, before that there was a pager system. Pager in the sense, it is a small device like this. If you want, you were used to sending SMSs, right? So this is called as a pager system, where you used to send short message services to somebody else. So just to read a message and send a message, there were pager systems in 98s and so on. So that is a 1G system. Then 2G came, where you were able to talk as well as send messages. And then your 3G systems came, where you were able to send MMSs, that is color images, photos that you were able to send. Then nowadays you have 4Gs, where you can send video calls, and 5G is coming, even 6G is also coming, right? So people are working on. So all this is possible because of the digital systems. At the same time, finally, the last limitation, advantage, your digital system, they are less affected by noise, because we are sending signals even to moon and even to Mars, right? So if you are sending an analog signal, they get attenuated. Say for example, if you are having an analog signal of magnitude, say for example, this value, because of atmospheric reasons, this gets attenuated. Attenuated in the sense, the strength of this particular signal, in fact, it deteriorates like this. Your attenuation will take place exponentially like this. So if I'm even a very simple example is, say for example, you are my neighbor. I can call you by just shouting. My voice is an analog signal. If you are 10 houses away, my sound voice will be slightly heard. If you are away to a next street, then you cannot hear my voice, however I shout. Why? What is that? What is the reason? It is because these analog signals or my speech signal, which is an analog signal, gets deteriorated or gets attenuated because of multiple atmospheric reasons. I will have a tree, I will have an electric wire, I will have a building, right? All these will try to suppress my analog signals. So this is the disadvantage of an analog signal. Now, what is the disadvantage of a digital signal now? This, I think I just discussed this few minutes back, that real world is completely analog. So our what we do is analog and what we want is also analog. All we need to do is we are processing everything in digital system because of its advantages. So if you want to process everything in advantage, then two main important things that you need to do is you need an analog to digital transmission at the input end, and you need a digital to analog transmission at the output end. And you have to make lot of effort in designing this short we call it as A to D converter and D to A converters. In short, we call it as ADC, analog to digital converter, and digital to analog converters. So you have to put lot of emphasis in designing these ADCs and DACs. So coming back to since we have understood well about the digital systems, now let us slightly focus towards the digital system. As you know, your digital system, they normally use binary number system. When I say binary, it means it has got two values. When I say bi means it is two. So binary means it is a two number system. What are the two number system here? We are having zeros and we are having ones. In binary system also, there are two logics. What I mean by logic is, somebody may say that I will consider 1 as my high and 0 as my low. Somebody will say I will consider 1 as my low and 0 as my high. So it all depends on, again, design engineers. But conventionally nowadays we started using 0 as low and 1 as high. And that kind of a logic is called as a positive logic system, right? So what is a positive logic system? Positive logic system means a logic system or a digital circuit that considers 0 as low and 1 as high. What is the other logic system? The other logic system is you have a negative logic system. In negative logic system is a system in which the digital circuit operate with 0 as high and 1 as low. When this will happen? When this will happen is, say if my analog signal that I am generating here is between 0 and 1, 0 and 1, then we call it as a positive system, positive logic system. If I'm having both positive and negative cycle, then this can be considered as 0 volts and negative voltage can be considered as high volts, right? So based on the logic that we are going to use, we can classify our system as positive logic system and negative logic system. I think this I have already said you. What is the real values of 0 and 1? What about 0.8 volt, 1 volt, 2 volt, 4.6 volts and 5 volts? As I said here, a value range in this particular range between 0 to say 8, we consider it as binary 0. Between 5 and 2 is a very low value, but still it can be considered. We call them as a binary 1. And the rest of the values between say 0.8 to 2, as in this diagram, they are not predictable values, they are high impedance values, and they are also called as an intermediate range where no value will exist. Okay, fine. So any doubts so far? Any doubt? Okay.
Sir, these ranges are set by the programmer.
Yes, these are mostly set by the manufacturers of digital systems.
Okay, sir.
Yeah. Okay. And fine, we are going to slightly complete the introductory part. So the voltage ranges, obviously, whatever may be the voltage, you are going to get the same kind of outputs. Now, coming to, since we are very sure that we are going to consider only digital systems, now we are going to slightly analyze the digital values. We said that this is 0 and this is 1. We do have meaning of these structure or these signals. In fact, these signals normally they are called as pulses. What do you mean by pulse? As you see here, it will not be so much wide. It will be very, very short pulse. It will be very short pulse like this, very infinitely short pulse like this. But just for the sake of understanding, I have drawn big here. So as we said, the digital voltage values have two states. This is high and this is low. These are called as pulse. This positive one, this high pulse, it is called as a positive pulse. And this low one, it is called as a negative pulse. Okay, there's a positive pulse and negative pulse. And in the positive pulse also, right? In the positive pulse, this one, the one that is rising from 0 to 1, this is called as a leading edge. The transition that is 0 to 1 transition is called as a leading edge. And when it is 1 and when it is transiting to 0, this is called as a trailing edge. So when it is transversing from 1 to 0, we call them as a trailing edge. And this is how a positive pulse will look. Negative pulse normally we consider 0 to be a negative one. So, but if you consider 0 and 1 as your limiting signal, that is 0 and low and high, then we call them this to be a positive pulse. A negative pulse will be this is going to be 0, this is going to be 1. Or it is the other way. So this is considered as high, this is considered as low. Okay, it all depends on how your AC signal is generated. So this will be your leading edge now, this will be your trailing edge. So 1 to 0 transition will be your leading edge. 0 to 1 transition will be your trailing edge in case of a negative pulse. What is it? Okay. Now, as you see in these diagrams, they are not going to be a perfect square wave like this. Practically what happens is, practically you will have your signals not perfectly in a square form, but in a slightly rising analog form like this, because all these are analog signals only, right? So there will be a slightly rising edge like this. There will be some kind of a transition that will take place, transient that will take place, and then it will drop linearly like this, and then one more transient will take place, and then again it will linearly like this. There will be a transition that will take place. So this is how your digital signals will actually look. So there are certain things that you need to understand here also. If the normal digital value here is this one, if this is what is we call it as a high value, or the 100% of your value here, your signal will slightly overshoot to 110%, and then it will come and settle down at 100%. This is called as an overshoot. All these are non-ideal pulses. Similarly, what is that we consider it to be this particular pulse width? When we say that this is an ideal case, this is a non-ideal case. What do we consider that this is the pulse width? The pulse width we consider it is from the 50% of the value. When the 50% of your value, we try to find out the line, vertical line, and then 50% of this particular signal during the transition here. This we call it as a pulse width. This pulse width is equivalent to the pulse width in the ideal case here. Similarly, you have different times also, the rise time and fall times. Rise time means from 10% to 90% the time taken, that is this particular time taken for your signal to rise. This is called as a rise time. And what is the fall time is from 90% from this particular point, from 90% to 10%, the time taken for your signal to fall is called as a fall time. So these are some of the definitions that you need to know. So All right. Okay. All right. So since I think we can wind up here. Okay. So maybe quickly I'll go through because next class we will start. So what is that you are going to study here is we are going to study about digital systems and what are the components of a digital system. When I say components of a digital system, obviously we are going to look at only zeros and ones we are going to look. When I say 0 and 1, it means that either it is true or false or it is yes or no. These are two digital systems. So, and there are multiple gates that you will be studying. You will be studying about different gates, AND gate, OR gate, and NAND gate, NOT gate, NOR gate, XOR, XNOR, right? And then the components of a digital logic include, we will be performing addition, multiplication, subtraction, division using arithmetic operations. We will perform addition and subtraction. Multiplication, division, we will be doing shifting and comparison based on this particular logic of shifting the bits and comparing the bits. You can perform multiplications and divisions. And you will be encoding your digital signals. You will be decoding your digital signals using a decoder. You will be multiplexing your signals, demultiplexing your signals. You will convert from one code to the other code. You will store your codes. You will count your digital signals. You will transmit your digital signals. All these things we will be covering in this particular course. So since again this is an introductory class where importance of digital system is being covered. From next class, we will start really operating on the systems, number systems in fact. So any doubt? Okay. So next what in the next class, we will start with the number systems here. Okay, so just a short information. Tomorrow at 10:30, you will be having the lab, and I will not be there. There will be lab staff here. They will be giving you the instructions on how to start. It will be just a very short period of time for tomorrow because you will be given task tomorrow. Okay, for the next week, from tomorrow to next week, that is tomorrow is 14 and next week I think it is tomorrow is 14 and 21. So that will be the week for which you will have to complete the experiments, and 21 we will all meet and then we will discuss what are the difficulties you will face. So tomorrow at 10:30 you will be meeting Dr. Upendra Kumar Pandey and then one senior lab technician and two TAs who will demonstrate you what are the expectations that you need to do for the next week. So thank you so much. In case no doubts, you may leave the meeting.
Sir, could you upload the